Section 5.4, we're talking about work. So if we think about work, most of the time we don't like to do work, but work is the total amount of effort required to perform a task. Right, so it's the amount of effort that we put into to perform a task. So if we think about it, maybe in the physics realm, we're looking at maybe push and pull on an object, maybe the force on an object as it's falling. So we're thinking about force, right? And so force, well, that is mass times acceleration. And so force is mass times acceleration. So then work is force times distance, or more precisely, however you spell distance, whatever, displacement, right, going in the same direction. So then as we look at force, our units for force, those are we usually use newtons, a way of measuring. So if we look at work as force, that'd be in newtons, and distance would be in meters. So then we have a thing called a Newton meter. So Newton meter, and that is called a joule. The other way of measuring it, so instead of looking at force has our newtons would have to be, it's mass times acceleration. So then if we look at, usually when a falling object, we have our mass times acceleration, which is a constant, which is 9.8 meters per second squared. Or if we look at weight, that already has acceleration in it. So if we look at weight as in terms of force, then we're looking at pounds. And if we talk about our distance or our displacement as feet, then we're talking a different kind of measurement. Instead of a joule, it's called a foot-pound. So that's another way to measure work, is either by a joule or by foot-pounds. Okay, so work is force times displacement, right? And so when we're looking at force, we can find that force is equal to mass times acceleration. In the book, it has, when we talk about acceleration due to gravity, that this g is 9.8, and that means that it stays constant, right? So it doesn't change. So work is pretty easy here when we're finding these equations. All it is just work, mass times our acceleration due to gravity times by our distance, whatever that is. So that's as long as our force constant stays the same. So as long as that stays the same, then work is pretty easy to find. You just have to times it by your displacement or your distance. But what if force changes? So what if force is a variable? So that means if I'm moving something along, the force maybe in between here is one thing, right? But then as I move to the next distance, this is a different force applying on my object. And then maybe a little bit later, I have a third force applying on it. So the force is changing. So if it's not a constant force, but the force is a variable, that means I would take the force of this plus the force of this one plus the force of this one, add those up, and then times it by my displacement, right? And if I keep on going, or if I make smaller increments, then I had to add up all those, add up all these, add up all these. So we'd have to sum all those up, right? So we'd have to sum up all those forces and add all those up, and then change it by our change in x, right? Whatever our distance is, our displacement is, right? Well, that kind of looks very familiar. something that we probably don't like to see, that kind of idea of the Raman sum. And if we take the limit of this as, x goes to infinity, so as we get smaller and smaller increments, smaller and 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 smaller, then we look at this as the integral, right? So the integral of f of x, and we just change that to the chain d of x, or dx, and then we go from a to b. So we can see this is not quite our force equation a little bit, because it's going to be changing with our distance in here, but we can take the integral of this and it will allow us to find work. So you can really think about this equation as kind of your work equation of this one right here, right, where this was some kind of constant, because really it's kind of like this one is your cross section, right? Oops, just your little. So yeah, so you can basically think of this f of x here as kind of your work equation, as kind of like a cross section. Okay, so this applies us to Hooke's law. Now Hooke's law is saying that if I have a spring, looks like this, it sits at a natural length, and then if I stretch it beyond that natural length, so here's my natural length, and it's stretched beyond that, whatever that distance is, it's proportional to the force that it takes to maintain that length. So Hooke's law says that the force that it takes to maintain that distance is proportional to the distance. So this right here, this k, is called the spring constant, and x is our displacement from our natural length. And so we'll go ahead and do an example here about how to use, how to find the work maintained. What work does it take to maintain this distance here? All right, so as we look at this, we're looking at a force of 40 newtons is required to hold a spring that has been stretched beyond its natural length of 10 centimeters to 15 centimeters. And then how much work does it take to maintain to go from 15 centimeters to 18 centimeters? Now we have to note that newtons are measured in meters, so we need to go ahead and switch this to meters. Switch this to meters, switch this to meters, switch this to meters. Okay, so as we look at this, as we switch this to meters, and this is just 0.1, this is 0.15, this would be 0.18, and so then we can look at it all in terms of meters. So here's my natural length, okay, at 10. So when I'm finding my force for this, that means I first have to find my spring constant. Okay, so I know at 15 or 0.15 meters, at 0.15 meters, my force that it takes is 40 newtons, right? And so then I can go ahead and enter that in, right? And now I can go ahead and solve for k. I know my x is just the displacement between 0.1 and 0.15, so that's 0.5. And so now I can go ahead and solve that, so k equals 800. So now k equals 800, so now I can write my force equation. And now I can go ahead and find the work maintained to go this distance. So that is the integral from a to b of 800x dx. Okay. And here my a and b is going from stretching the 15 centimeters to here. So that's starting at 0.15. Or what's the displacement here? So that's 0.05. So the displacement from here to here is 0.05, and the displacement all the way across is 0.08. So my B is 0.08 because I'm looking at just my displacement of the spring. So to here is 0.5, and then all the way across is 0.8. Okay, so then I can take the antiderivative, so that'd be 400x squared from 0.05 to 0.08, and I plug those in. Oops. And I get 1.56. And because I'm in newtons and I'm in meters for my distance, that this is in joules. Okay, so as we look at another equation, or another question, we're looking at a 200-foot cable, and we're looking at it's hanging off a building. So here's my building, and this cable is hanging off of there, and that cable is 200 pounds, and it's 100 feet long. So that means it's stretching. This distance right here is 100. So that distance is 100. And that means it's 100 pounds. That's how much it weighs, and we want to know how much work it takes required to pull that to the top. Well, here, if we think about maybe cross sections, if I take a cross section, how much is it going to take to get that cross section out? And then we can just go ahead and get more and more cross sections, and so that means we're going to take the integral. Okay, so well, if it's 200 pounds and 100 feet, how much does 1 foot weigh? Well, 1 foot would weigh 2 pounds. So it's 2 pounds per foot. And now that we're in feet and pound, our answers are going to be in foot pounds. That's what our work is going to be labeled in, is foot pounds. Okay, so now we want to know how much force it takes to get out here. So if this is my change in x, then I have to pull this out all the way. So what's the distance that it has to go? Well, it has to go 100 feet if I pull from the bottom, but my cross section might not be at the bottom. So even though the bottom of this cable is at 100, how much is just this distance to right here? Well, that distance is just x, or you can say x or y or whatever you want. Okay, so the distance that I have to take this little cross section is a distance of x. And so now I know my force is equal to 2, because it's 2 pounds per foot, and then however big I want my cross section, so the change in x. So 2 pounds times the change in x, or dx, whatever. And then I have to times that by my displacement, right? The distance that I have to travel. So that's just going to be x. So then I can go ahead and take the integral of this. So that would just be 2x, and then change in x is just the same as dx. And then I'm taking it from 0 to 100. So now I can just take the integral of this. So that's 2/3 x cubed from 0 to 100. Don't have to worry about plugging in 0 because that's going to be 0. 100 cubed times 2/3. Not 2/3. I don't know why I said 2/3. That's only an x, so this should be only squared. So this should just be x squared, sorry. X squared. So that is 10,000. Sorry about that. And so that is foot pounds. So it's going to take 10,000 foot-pounds to pull up that 200 weight, 100-foot long rope or whatever it is. All right, so here's the more complicated that you're going to get. So if we have a cylindrical tank, and we are taking this tank, and we want to It's filled up with water to 8 feet, and we want to pump it out, and we want to see how much work it will take to pump it out. Okay, and so we know this distance here is 10 meters. It says it's 10 meters. And we know we're taking it out to the effect of it's filled up to 8. And we know the radius. The radius is 4. So again, if we do a cross section here, and we do a cross section, maybe in between here, we don't know what this radius is, but we do know what the height is from here to here. We know it's 10, right? So we kind of have two triangles in here. We have one triangle with a radius of 4. Oops, sorry. Undo. So we have one with a radius of 4, and it goes down to 10. We have that one, and then we have one inside of it. We don't know that one. That one's R. And then up here, we know this is it's X, because this distance is all 10. So this distance in between here up into it is X. So this distance at the bottom would be 10 minus Rx. So this is 10 minus Rx. Now we can set up a proportion because these are similar triangles, right? They share the same angles. So we can go ahead and set up a proportion for R. And so we have R over 10 minus X is equal to 4 over 10. And so now we can go ahead and solve this for R. R is equal to 4/10 over 10 minus X. So there's our radius. And so now we can think about, we're talking about water, so that means we're talking about volume. So then we have volume for a cylinder, volume for a cylinder, actually volume for this shape right here, this cross section, because we're taking a cross section, is pi r squared, because it's in the form of a circle. So pi r squared, and then times by the height of our cross section, or the change in x. So now we know our r, so we can go ahead and plug in our r. And we can really just factor out that 4/10 and put it on the outside. That's fine. And then 10 minus x. Actually, that's being squared though, sorry. So we can change that a little bit. So this is being squared, and this would be squared. So 16 over 100 times by the change in x. So there's our volume for that cross section. Now we have to pull it out, right? So we have to go that distance of x. So, but first, we want to rewrite this in terms of mass and acceleration, right? Because that's what force is. So I can reduce this fraction by 4, right? So 4 over 25. Okay, so if you don't know, mass is volume times density. So, and then the density of water is 1,000 kilograms per cubic meter. And so we can go ahead and just take this and multiply it by 1,000, and it will get us our mass. Okay, so then we can get our mass. So our mass is going to be 160 if we reduce 160 pi, and then times 10 minus x squared times change in x. So there's our mass. Now we can multiply it by acceleration to find our force, because force equals mass times acceleration. And our acceleration due to gravity is 9.8. So times 9.8. So then we get our force is equal to 1,568 pi times 10 minus x, quantity squared, times the change in x. Now we can go ahead and times that by our displacement, which is x. So then we have our force equation. 1568 pi x, or x pi, whatever. And change in x. Sure. Now we can go ahead and write our integral, because now we have our force equation. We change our change in x to dx. And then where we're going from here, we are taking it from 2 meters to 10 meters. Because as we look at our, oops, if I can draw. Nope. So we look, nope, still can't draw. Sorry about that. Because at the very bottom is 10 meters, and we're taking it all the way up to 8, right where our water level is. So our water level starts 2 meters down. So that's why there's going to be a 2 here. All right, thinking right now. So there it is. And so down here is 10, right? And up here is at 8, but we have to take it from the top all the way out, right? So, well, this way down is our water level starts at 2 meters down, and it goes all the way to 10. So that's why it goes from 2 to 10. All right, so now as we integrate this, we can go ahead and FOIL this out and take out the 1568 pi, and then we can FOIL out this. So 100 minus 20x plus x squared, distribute the x. So then we get 100x minus 20x squared, and then plus x cubed dx. And we're going from 2 to 10. So then we can go ahead and integrate that. And 1568 pi. And then so that is 50x squared minus 20 over 3 x cubed plus 1/4 x to the 4th. And we're going from 2 to 10. So you plug in 10, plug in 2, a lot of work on your calculator, but you get something that looks like this. That's a 6 in there, that's a 5, that's not an I, it's a 1. Pi. My little pen is not working, but we're almost done with this video. And then 2068, or 48. So 2048. Sorry about this. Come on, pen. 48 over 3. So there's that. And then your last part, you can convert that to 3.4. 0.4 times 10 to the 6 joules. And there, you're done.